Okay, this is an example problem for Physics 1000, Auburn University, summer 2013. In two previous videos, we've tackled this circuit to answer two different questions. In the first one, we calculated an equivalent resistance here, and in the second video, we used that result to calculate the value of the current here, which we found to be 9/25 amperes. So in this video, we're going to delve a little bit deeper into what's going on with the resistors. I'm going to ask, what is the voltage drop across R1? If we're using our gravity analogy, this is sort of, the resistors, remember, are sort of analogous to your hills as far as voltage is concerned. As you go down a hill, you find a reduction in your gravitational potential from the top of the hill to the bottom of the hill. And in the analogy here, that's how resistors sort of work in this circuit. As you go across a resistor, you're going to find a reduction in your voltage. And so the question is, how much is that voltage reduced as I go across R1? So the tools we use to solve that, number one, are the results from our previous videos, or at least the current here, and good old Ohm's law. Ohm's law is super important to these types of problems. And most circuits in our everyday life follow this law pretty well, so it's a good thing to know. So I'm curious about the voltage drop in R1, so I'm going to rewrite this and I'm going to subscript it. The voltage drop across R1 equals the current going through R1 times the resistance of R1. Of course, we know from our discussion of series circuits that I1 is just I. In a series circuit, you expect to find the same current no matter where you look. And that's simply because it doesn't have anywhere else to go. If we go back to our mechanics analogies, if I pump water through a hose, but at some point my hose splits, sort of like this, then the water that's coming through here has two different paths to take, and in general it's going to take both of them, and some of it's going to go that way and some of it's going to go that way. And that's not the case here. What we have here is just a straight hose. So the water has nowhere else to go. Even though I'm putting stuff in here, maybe there's a kink in the hose, and maybe there's something it has to go through here, a filter or something. Even though I'm putting some obstacles for it, it still has nowhere else to go but this way. It can't branch off, it can't go this way. It has to go down the hose. So, coming back to electricity, that's exactly what's going on here. The current everywhere has to be the same because there's nowhere else for it to go. So now to find the voltage drop across R1, I just plug in some numbers. Coming up here, this is going to be 9/25 amps times 10 ohms. You can reduce this down to the 10/25 is going to be a 2/5. That's going to get me 18/5 volts. An ampere times an ohm gives me a volt. So, I believe I did that right. Yep, I did. 18/5 volts. So the voltage drop at R1, you would find 18/5. Well, 18/5 volts dropping over R1. And I could do the exact same for R2. I could plug in the voltage drop across R2 equals the current on R2 times the resistance in R2. In fact, why don't we do that? Let's go. I'll go to the next page because I want to keep this. The voltage at R2 equals the current in R2 times the resistance of R2. And I'll just plug in the numbers here. The current is still 9/25 amps. And the resistance, I believe, is 15? Yep, okay. Times 15 ohms. And if you run the numbers, this is going to reduce to 3/5. You're going to come up with 27/5 volts. Now, I want to show you something really interesting. What we've said is that the voltage drop, let me go to a clean page. The voltage drop across R1 was, I believe, let me go back, 18 over 5. Now let me draw the 8 where you can actually read it. 18 over 5 volts. The voltage drop across R2 was, I believe, 27 over 5. Yep. 27 over 5 volts. If I add these together, I'm going to add V1 plus V2. I get 18 over 5 plus 27 over 5, which is going to be 45 over 5. I'm sorry, I should really be using units here. If I'm going to ask you to do it, I should do it too, right? Which is, if you reduce this fraction, it's 9 volts. Let's go back and look at our battery. Look at that. Our battery here is 9 volts. If you calculate your voltage drops across every resistor, and then you add them up and you come up with something different than your original voltage, you've got a math mistake. This is exactly what you'd expect. The voltage, as long as it's not, leaking off anywhere, has to be what we started with. It has to be 9 volts. So immediately you should say, aha, I can take a shortcut, especially if I have a circuit where I have, 8 or 9 of these guys. I want to save myself as much time as possible. So in this case, we actually calculated the voltage drop across R2, but we didn't have to. Once we'd calculated the voltage drop across R1 as 18 over 5, if I know that all my voltage drops have to add up to equal my original voltage, to calculate the voltage drop across R2, instead of plugging in the numbers here, which you absolutely can do, instead of doing all this mess, all you have to do, sorry, I'm getting ahead of myself. That's not R. This is the voltage across R1. All you have to do is take your original voltage, which is 9 volts, and subtract whatever you've already got for R1. And sure enough, if you work that out, that's going to be 27 over 5 volts. There's an awesome relationship here that you can use to make these problems easier. So hopefully this made some sense to you. If it did not, please email me or come talk to me. I'd be happy to talk to you about it in more detail. So that's voltage drops across resistors in a series circuit.